We've been looking at these questions involving some combinations of charge at the corners of a square, three corners of a square, and we're asked to find the force on charge B due to charge A, the force on charge B due to charge C, and the net force on charge B in each of these examples. So let's see how we can go about doing that. Conveniently, charge A and charge C are located at right angles to each other with respect to charge B, so these will break down pretty nicely in a coordinate system that uses an x, y orientation here. So let's first take a look at the example A, and you can generalize the method from here to the other three examples. So I see that I have three charges, a positive 1 nanocoulomb, negative 1 nanocoulomb, and positive 2 nanocoulombs, and nanocoulombs are just a billionth of a coulomb, 10 to the minus 9 coulombs. So if I have charge C is positive, charge B is negative, I know those are opposite, so they're going to attract. So on charge B, we're going to assume here that charges A and C are fixed. Charge B might be fixed as well, but it's experiencing force due to these two other charges. So what is that total force? I know this force will be attractive and in this direction due to charge C. And since the force is proportional to the product of the two charges, whatever size this force is, which is proportional to 2 times 1, this force in the y direction is going to be half as big because it's just proportional to 1 times 1. So let's see how big the force between A and B will be, the force on B due to A. So the force on B due to A, we can call it FBA, is going to be, using Coulomb's law, KE Q1 Q2 over the distance between them squared. What is KE? Well, we know it is 9 times 10 to the positive 9 Newton meters squared per Coulomb squared. Then charge A is going to be 1 nanocoulomb, so that's 1 times 10 to the minus 9 coulombs. Charge B is 1 coulomb. I'm just going to use the magnitudes here because I already know the direction. That's the only thing that I care about with the sign of each charge. So charge B is also 1 times 10 to the negative 9 coulombs. And the distance between them, I notice that my Coulomb constant here has meters in it and coulombs. That's why I couldn't use nanocoulombs here. I need to use an exponent and actual coulombs so that my units work out correctly. Similarly, my distance here is given as 5 centimeters, but I need to have a distance in meters, so I know that this distance will be 0.05 meters, and we're going to square that. So fortunately, these numbers will simplify pretty nicely. 10 to the 9 times 10 to the minus 9 is just 1. So I have 1, and 9 times 1 is 9, and a 10 to the minus 9 still. So our numerator looks like 9 times 10 to the minus 9. My denominator, I see that this is 5 times 10 to the minus 2 squared. So that is 5 squared times 10 to the minus 2 squared. So that's 25 times 10 to the minus 4, or 2.5 times 10 to the minus 3 meters squared. What are the units in my numerator? They are newtons times meters squared, because I've canceled out my coulombs. So now I see I'm going to cancel out my meters as well. And let's see, if I divide something by 25, that's the same as multiplying by 0.04. So dividing by 2.5 is the same as multiplying by 0.4. And I have 10 to the minus 9 over 10 to the minus 3 here. So this works out to 3.6 times 10 to the minus 6 newtons. Or you could call that 3.6 times 10 to the minus, well, just 3.6 actually, 3.6 micronewtons. A micronewton is 10 to the minus 6 newtons. So that is the magnitude of the force between A and B. We already know, fortunately, that the magnitude of the force between B and C is just twice that big, and it's in that other direction. So the force between force of C on B is just going to be 7.2 micronewtons. And what about that direction? Well, let's come back to our diagram here. I know that the net force is going to be the vector sum of these two forces. So how do I calculate that? Well, the vector sum, to get F net here, is just going to use the Pythagorean theorem. So what does that look like? The magnitude of F is going to be the square root of the sum of the squares of the two forces we just found. So that's the F in the x direction squared plus F in the y direction squared, all under the square root. So I see that that is the square root of 3.6 micronewtons squared plus 7.2 micronewtons squared, and you can work out what that works out to. Similarly, if we want to know the angle, we have a simple trick that will work. I want to know this angle right here. Well, I see that the blue is the opposite side of the triangle and the green here is the adjacent side. So that angle is going to be given using an inverse tangent. So this angle, we'll call it theta, like you do. That angle is going to be the tan inverse, or arctan, of Fy over Fx. And that is how you find both the magnitude, the components, the magnitude, and the direction of that force. When you look at these other examples, you should see that the only thing that differs is the sign of these charges. So that's going to have an influence on the direction, and you'll need to do some reasoning about first, second, third, fourth quadrant ideas to figure out the direction of the force on this charge in each of these four cases.